All right. Welcome back to another episode of Bio to Bedside. Jeff, how you doing today?
I'm doing great. Dude, that song is stuck in my head. I couldn't figure out, like, that little tune is always in my head, and I'm like, what is that from? It's the podcast intro song. We got to make our own intro video. That'd be so much fun. We
Yeah,
should
it
do
would be
that.
better than
Make it a
just a
priority,
random countdown. Yeah.
even though it's catchy.
Yes. Excellent. All right. Well, everyone, welcome back. Really excited for the conversation today where we're going to be asking the question, how do you get very large genetic payloads into very specific places? This is a challenge that, go ahead, Jeff.
Genetic and peptide payloads. Don't
Right.
forget peptides, because it
Yes.
can do this too.
Right.
Which
But
was,
but ultimately that's the challenge, right? Is how in the world do we get such large pieces of important, either genetic or protein information into a very specific part of the body? And that's why we're pretty excited to have Brian on today to discuss the innovations that they've developed in that area and the therapeutic potential they see for it. But before we get started there, again, folks, the format for today, right? We want this to be a conversation with you. If you have any questions at any point, feel free to ask them in the chat, and we will get to them as quickly as we can. In the meantime, just as we're getting started here, let us know where you're coming in from around the world. It's always cool to see people from India, people from Europe, people from all over the States coming in. So please let us know where you're coming from, and we'll get started in just a minute here with Brian. Just as we're waiting here, Jeff, so obviously where we've seen so far is it's really easy to get a small peptide or a small piece of genetic information into different parts of the body. Where do you see, what has been the challenge? Like, what's been the upper limit that you've seen so far?
well, so I forget. Oh my gosh, I'm forgetting his name. We had on Andrew from
Andrew Bardinsky?
Yes. But anyways, they're doing like electroporation for ex vivo cell stuff, and
Andrew Mancini, different Andrew.
yeah. Sorry. But one of the things in that conversation was that, LNPs are good for DNA, LNPs are good for RNA. Things like AAV and other kind of viral delivery systems are good for DNA. And there's not a whole lot really for protein delivery other than just like straight up protein injection delivery like that. But getting payloads delivered to cell specific payload delivery is very important, especially with things like in vivo CAR T, right? And like, for example, one of the major limitations of in vivo CAR T over a ex vivo CAR T is that the in vivo CAR T is limited in the payload capacity. So you can't just like shove in all kinds of different like expression cassettes, because you're going to max out your delivery vehicle really quickly, and it limits the overall like dynamicness of your therapy, because you can only have, you can deliver the CAR gene, for example. But if we can be delivering cell specific delivery of large genetic payloads, large protein payloads, that changes the game for all kinds of different reasons. One of, obviously, Brian will get into it, but like, we'll be limiting toxicities. You increase the efficiency of your delivery, so you need to produce lower doses per patient, because you're not going to be having it diluted all throughout the body. You can have, all kinds of really interesting stuff. But yeah, one of the major limitations in the therapeutic payload delivery space is cell specificity, and getting a delivery vehicle that can give you that cell specific activity, but is also not super tiny, right? You need to be able to bring a lot to the cells. And it's my understanding that that's kind of what Carrigent is doing very well.
Excellent. Very good. So we'll bring in Brian in just a second. So folks, again, we'd love to see where you're coming in from. Glad to see Seattle, and then Stuart over in California, right on at Berkeley. We've got a West Coast concentration right now. That's interesting. So thank you for waking up first thing in the morning and spending some time with us. All right, we're going to bring in Brian, and we'll get started. Brian, welcome to Bio to Bedside.
Thank you for having me. Glad to know you're kind of excited to have me. You said in the intro.
Of course. Excellent. So yeah, just to get started here, can you give us a quick overview of who you are and what you do?
Yeah, sure. Brian Newsom. I'm CEO of Carrigent, as they mentioned. I've been in the cell and gene therapy space my entire career, so I've been there a little over 30 years. I live in Georgia, but our company's based in California, in the Los Angeles area, and got a great crew there working in an incubator, working on technology development, and as you mentioned, developing our cargo platform.
Excellent. So I guess from your perspective here, Brian, what has been the challenge that's kind of held back advanced therapeutic modalities from being able to deliver large cargoes?
Well, I think it's just the tools we've had to use, right? I mean, they've been great to date. AAV's been around for a long time, but it's very capacity limited, and that's been one of the big issues, right? So, if you look at it, AAV can handle about 4.5, 4.7 kb, depending on the serotype, and that's good enough for many genes, right? About 80%. There's two problems with that. One is there's still 20% of things you can't do. But the other part is, even when you can handle the whole gene, you can't handle everything else you need, because a lot of these genes need regulatory elements or need something else with it, right? So if you max out with the gene and you don't have room for some of the other pieces you need, you really still have a very inefficient system.
People underestimate that. I think that even when it comes to my brain always goes to in vivo CAR T, getting good expression in various cells. It isn't like you can use a viral promoter, for example, but if you want to get like dynamic expression or anything like that, you need to have these nice regulatory regions, and it adds bulk to your payload.
Exactly right.
So yeah,
cell-specific promoters, safety switches, a lot of these things that people don't have room for in a traditional AAV, and some of the reason I think we have some of the problems we do with the AAV. And I think we can alleviate some of those issues with the system we've got.
Awesome. Well, one other thing, just quickly, Christian and Preeti, thanks for coming in from Germany and then from Philadelphia. We're getting a bit more rounded out through the time zones. This is awesome. So we've got people first thing in the morning waking up, and then people who are finishing off the day. Glad you can join us. So again, we're speaking with Brian Newsom here today from Carrigent, really with regards to how we can solve the delivery problem that's kind of plagued cell and gene therapy with regards to large payloads. If you have any questions, by all means, feel free to ask them, and we'll get to them as quickly as we can. So I guess just moving on from there, Brian, can you tell us, your goal here is to develop therapeutics. How did you start to develop these technologies? Where did it come from?
Yeah, so about a year and a half ago, Robert and I, my co-founder, were working in another company, and his goal there was to develop some technologies around viral expression and viral expression systems. So was working with him on some of that work, but then we ended up spinning out a company out of that one and to become Carrigent. The goal was to continue that work, right? Working on viral vector manufacturing, working on viral technologies. And so we developed several platforms there. We have a new HEK line that's gene modified for high expression of large cassettes. So we can do lenti cassettes that are 7 to 8 kb and get commercializable titers there. We have a expression system enhancer where we can get better viral titer regardless of which system you're using. We've got an enhancer for the use of virus where we can get better use of that, lower your MOI of virus, things like that. So those are the things we were working on, and we were kind of being a CRO at the time, doing work on the service side to help people with optimizing their systems. At the same time, one of the things Robert had been working on for a number of years was trying to get directionality out of capsids, right? Re-engineer capsids to get them to go where you want them to go. And had kind of decided that was not working well, wanted to find a way around it, and started thinking of CAR T, right? CAR T is great because that's what it does well. It directs cells exactly where they need to go, and then the normal machinery kicks in and it does what it needs to do. So he said, why couldn't we use that as the guiding system? But in order to do that, we needed to move away from viruses or particles and move into using cells as a delivery mechanism. So a couple people have tried that before. It's been around for a while where people have said, let's use cells because there's a lot of advantages to that, right? But hadn't been able to get it to work. So Robert really came up with, I think the crux of it is the way we can kind of decouple the directionality and the delivery piece and do the technology that he used kind of inside the cell, the way we manufacture that to make it work right, some secret sauce there. And part of that was the HEK line we're using to create these large cassettes that gives us the real estate to help do the engineering in the cell. So, long story short, we use SCFPs to direct the cells, and then we have decoupled from that through an inducible promoter the way to generate what we call cargo, which is the payload plus the translocation mechanism. That way we can move whatever payload you have, we can hook onto it and move it outside the delivery cell and into the target cell, into the interstitial space, into the nucleus, wherever you want it.
Now, does the capacity of that vesicle matter at all, or is the packaging consistent across the vesicles, or is it just kind of like you can have all kinds of different payloads and you're going to get a relatively decent encapsulation of them, on aggregate, or is your payload capacity still limited to the capacity of the actual vesicles?
So you mean the transport from outside of the cell? No, it doesn't seem to be. So yeah, we're using transport peptides, and the way they work, they seem to be fairly size agnostic. Now, what we don't know, and I won't say we've tested everything yet. We're still pretty young, right? So we haven't tested the ability to get really large payload into the nucleus of the new cell. So like 15 kb inserts, right? We know we can technically generate that. We know we can kind of move it around, but whether or not we can in vivo get that from our cell into the nucleus of the cell, get functional transcription, translation of the protein, haven't done that yet. In theory, yes, we can, right? And we see how that works at small scale, but there may be some limitations in size there when we get to that big of a payload in getting it moved exactly where we want it and getting it to be functional. So we've done kind of moderate size. We can do what we know is larger than what the AAV can do, 5, 6, 7 kb. How high we can go, I think, still to be determined.
Is it big enough for antibodies?
Most likely, yes. I would think so. We haven't tested antibody. We've done protein, but most of those have been small protein to date. So, but I don't see why not. So
there's potential to do intracellular delivery of antibody therapeutics.
At least antibody fragments, yes. Functional fragments of antibodies in minimum, I think. Yes.
That's really interesting.
Yeah, we haven't even scoped out all the potential uses yet. We're still working on that and have areas we want to go in, but still a lot of things for us to look into as well.
Interesting. I have questions about enabling technology and competition and things like that, but we'll hold those off for a little bit longer.
Okay.
I'll let Ben take over here. Otherwise, we're just going to go down a rabbit hole.
Well, yeah. If we're kind of zooming in back to something you mentioned a little bit earlier, right? You're talking about deliverability versus targeting. Can you elaborate a little bit more about the difference there? Where have existing solutions failed there?
Yeah, so existing solutions, I think both, right? I mean, most people that were trying targeted delivery with cells weren't necessarily using an scFv. This is kind of, a lot of this came out even pre-CAR T, right? So they were using cells as like MSCs as a way to get in the body and as a way to move things around. But I don't know that the targeted delivery was there most of the time that work was being done. But for us, it makes it easy. For one, scFvs are a pretty well-known entity now. Easy to get. The hardest part for us is we're typically trying to deliver to normal cells, not to cancer cells. And most of the development of scFvs have come in the cancer realm, right? Yeah. So we have to kind of go out and look at what are cells of interest for us, what are areas we want to deliver to, and how do we make scFv to very targeted locations. So for instance, CDH15 is one where we can deliver specifically to cardiac and skeletal muscle, which is a great target for DMD, right? Mm. So that's one where we can get away from all the other cells in the body. We can even get away from smooth muscle because it's not really necessary, very targeted delivery. But some are more difficult, right? Some cells are really difficult to figure out how to target, and how do you get something very specific? So, because again, if you don't have an antigen, we can't deliver specifically either, right? You've got to have something to target, some sort of extracellular antigen to target. So I think that's, where some others have failed. The other part is, like I said, kind of the decoupling of the two pieces. We have an inducible promoter for the cargo generation. And then the advent of some of these new kind of translocation technologies, translocation peptides, has enabled us to get very specific delivery of being able to move it outside of the cell we're working with, and whatever delivery cell it is, MSCs or whatever cell we're using, and then into a very specific location within the other cell. So, we're benefiting from the fact that a lot of these things have developed over the last 10 to 15 years, and all these technologies are kind of available now where they weren't to prior people that have tried this work.
So it's not T cells you're using?
Not typically, no. I mean, we use typically MSCs, and a lot of reasons for that. One is they're very easy to grow. We can grow them in large numbers. We can grow them quickly. We can grow them cheaply. The other thing is they're very highly transducible. We can get 90+% transduction efficiency. And if we need to do a dual vector for some reason, we can still get 80+% efficiency with even dual vectors. really easy to use that way. And allogenetically, they're really, I wouldn't say totally immune privileged, but they don't cause a big immune reaction. They're very easy to use. We don't have to gene edit. We can put them in an allogenic sense, and they'll survive for 4 to 6 weeks, enough to get the job done, and then they'll quietly go away.
It's probably like a built-in safety mechanism almost, where it's like the therapy is going to dilute itself over time just from being rejected.
Yeah, it does. And we can also add, like I said, because we have larger real estate, we can also add mechanisms to get rid of it sooner if we need to. We can have suicide switchers and things like that. Yeah.
And how about feasibility of redosing? Does the immune privilege kind of break down after the first dose, or is it relatively stable?
We'll see. If we have to redose and we can't do it with the same donor, we can always move to another donor. It's going to be HLA specific. So the likelihood is we could redose, because a lot of MSC regimens have been able to redose without a problem. Mm-hmm. But if it does become an issue for some reason, we can always move to the donor.
Right. And how is the infrastructure around allogeneic MSC production?
It's actually pretty good. MSCs have been used for about 30 years, so they're really safe to use. A lot of people have done it. There's a lot of people that are using it. Not many commercial therapies, because the one thing lacking with MSCs has been efficacy, right? People have tried to use it in a lot of ways, and they just haven't been able to do the job. It's not been a safety issue. So I think what we've seen is that, we have a lot of safety data behind us, and all we have to do is add the efficacy, which is what we can do with our system.
So it's a CAR MSC payload or therapeutic payload delivery vector, basically.
Pretty much. And we have a CAR MSC too, which is actually a killing. So we can add a killing mechanism to it. So we're doing this like in the CD19 context for, 2 reasons I think we can be better than a CD19 CAR. One is we're allogenic, so we don't have to worry about the manufacturing issues of people that have been through all this, preconditioning. We can use an allogenic sense much easier than we can do T cells in allogenic sense, because we don't have to do the gene editing. The other one is that we don't kill B cells. Our mechanism of killing is using thymidine kinase, and thymidine kinase only kills dividing cells. So if we go into a CD19 context, we can kill the tumor cells without killing the B cells.
Interesting. Huh.
That's actually the first asset we're developing.
So this is probably a very bad question. I consider myself to be a cancer immunologist. Non-cancerous B cells aren't dividing?
Not rapidly.
Not typically?
No.
Okay, not rapidly.
They'll be dividing to a certain extent, right? But you've got a lot of B cells that are fairly, I wouldn't say they're dormant, but they don't divide rapidly.
Sure.
And so for the time of activity that you would have these cells in there over a couple of weeks, you're going to be reserving a lot of your B cells. Not all of them.
So how would you properly classify this, right? You're using a whole cell to deliver a specific payload. Would you say it falls more in line with a cell therapy or a gene therapy, or is it in between somewhere?
Yeah, we're right in the middle, right?
It's a Venn diagram.
It is a cell and gene therapy.
It really is. It's about the best kind of combination you can think of, right? And
that's
So I thought about the same thing, and we're truly kind of bringing the two together. So often people put cell and gene therapy together, right? But they're really two fairly different modalities in most instances. In this one, it's truly, we're putting it together. It's a cell and gene therapy.
So why do you think people haven't looked into this approach before? Why is it that you are the first people using it?
I think some people have. There have been some people, like I said, that have tried to use MSCs in this context. I think the technology to make it work well was just not out there. And there's a lot of things we've done, I think, on the technology side that Robert has done to make this work efficiently and effectively that just weren't available before. Either, people didn't know how to do them, or they just didn't, quite do it right. Robert's got this down to where it's actually working extremely well. It's a highly efficient system. And we're still working to raise efficiencies in this. How efficient of delivery can we get? We don't know exactly on that, but I think, like in a lot of cases, the tools just weren't around even 10 years ago for some of this. And it took kind of somebody coming by with the idea at the right time and understanding what was available to them to make this work.
Now, is there any kind of magic sauce to the, I keep forgetting what you're calling it, the transport vehicle, whatever it is. Is that proprietary, or is that a relatively well-known system that you're taking
some of these, there's some of that's pretty well known, and delivering things like proteins is pretty easy, right? Because we can get a peptide attached on the end of the protein pretty easily. Delivering DNA with that can be a little more tricky because you're asking a peptide to basically link up to a strand of DNA.
Sure.
And so you kind of have to engineer that piece in, which makes it a little more difficult. We're also looking at doing, like in vivo gene editing, where we have to latch onto an entire complex that has RNA, DNA, and protein all together and move a very big complex that way. So that can get tricky on the transport side. So and I won't say we worked all the details on those really big moieties, trying to get that done, but we have, on paper we've worked it out, right? We know how to do it, so physically make it work now. But I think that's been one of the trickier parts when it's a non-protein packet to deliver.
Yeah. I'm surprised that there probably is. There's probably some kind of like a chemical linker that allows you to link nucleic acids to peptides. That must exist. Yeah.
Yeah, you just got to make sure you're not damaging the integrity of the peptide or the DNA. Everything's in the right orientation. All that. So there's a lot of the devil's in the details, as they say, right? So there are ways to do it, but you got to make sure it's doing it right.
Yeah. So what are you, this is probably a loaded question, but are you more interested in doing peptide therapeutic payload or nucleic acid therapeutic payload delivery?
Nucleic acid in the long run. Our first one will be a peptide because it's the thymidine kinase, because it's kind of a low-hanging fruit, right? But in the long run, we're looking mainly at monogenic rare disease. So we're looking at both, gene replacement and gene silencing. Yep. And that's really the big market we want to go after.
Interesting. So like what is the upper, just to rephrase for anyone who might be coming in now, what is the upper limit of what you can deliver if you're using basically a whole cell as opposed to a tiny AAV vector?
We don't know the upper limit. I would say with our manufacturing scenario the way it is, for DNA, 10 kb-ish right now is where we are, but we have a second way to manufacture where we can move above that into larger stuff. Right now, the theoretical limit is probably in the 30 kb range, though. So, pretty large, right? I mean, more than we really need to do. The largest, the largest gene there is dystrophin at 14.2 kb as far as coding sequence. So we can't really see needing to go above, 16, 17 to get that plus a couple of regulatory elements in it. And whether or not we can do that, speculating we can get there. But we certainly know we can do like 10 kb.
So here's a question, and I'm probably gonna botch this. I'm thinking of it on the spot. So, what do you say to the critique that the advantage of in vivo gene editing is you don't have to actually produce a cell therapy, and you can produce like a gene editing therapy vector, and that avoids all of the mess of doing a cell therapy. So, what is the purpose of having a cell therapy to deliver a gene therapy? Why not just make the cells?
It's really still the targeting mechanism, right? I mean, because when you're doing anything in vivo with a virus, the targeting is still the problem. So just like in vivo CAR T, if you're doing it with just a lentivirus, it's still how do we get it where we want it to go and only where we want it to go, which is oftentimes the bigger issue. You can often get it where you want it to go, but getting it to not go where you don't want it to tends to be the issue. Sure. So just like with AAV, everything's going to the liver, causing acute liver failure. That's why we've had the problems we've had with some of the toxicities. So getting it to go in a specific area has been very challenging with any sort of virus particle, in vivo system like that without using a cell.
Yeah, and sorry. So that's the more that I thought about it, that was kind of a dumb question because I'm so like an oncology guy, and immediately I'm like, oh, in vivo CAR, and if you're making a cell therapy to deliver the CAR construct using a CAR, it's kind of like, what are we doing here? It's kind of circular, but you're not doing that. You're doing things like delivering it to muscular tissue or bones or neurons we'll get to the neuron thing later. But, so that was kind of a dumb question. So I guess what you're saying is that we can get these things to deliver to very specific cell types, whereas the other forms of gene delivery vectors are kind of messy. And that's like the major advantage of this.
Yeah, I mean, our two big advantages is the unlimited size or fairly unlimited size. It's larger, but the bigger one is really targeting, right? Getting it where we want it to go. And in the intro, you kind of mentioned the other advantages that gives you, right? by giving such specificity, we can give lower doses. By giving lower doses, we automatically have lower toxicities, lower cost, things like that. So that specificity is great for what it can, not do in the toxicities, but it's also good for a lot of other things as far as the economics of this.
That was one of the things that I realized would be a benefit with like tumor activated masked like peptide therapeutics, because the thing's not being diluted by binding to the receptors around the body. It's only being active in the tumor. You get to use lower doses, and it reduces your COGS and everything. And it's kind of like a secret advantage to these kind of things.
Yep. Yeah. If you look at things like a typical AAV9, right, about 5% of that actually crosses the blood-brain barrier.
Right.
And so you're getting a 20x dose just to get the little bit you want to trickle across the BBB. So if you could lower that and say, if we have a much, much higher efficiency, can we give a much lower dose? Because like all of our stuff is going where we want it to go, as opposed to just being diluted and going around the body.
Exactly.
And unfortunately, with viruses and particles, no matter how much you engineer, they've got a certain tropism, they've got places they want to go. And for the most part, they're kind of ubiquitous expression around the body, right? They're going everywhere. The targeting they're doing helps them to bind places. It doesn't necessarily work as a trafficking, though, and get them to go certain places.
Right. That's true. And being a living cell, what is like the motility of the MSCs? Are they relatively like mobile?
Yeah, they're not great at crossing the blood-brain barrier, right? But everything else, they're great. They're great at infiltrating tissue, things like that. So people have been able to do a lot of MSCs as far as going throughout the body.
Nice.
We think we can do IV delivery for most things. We can even get them to cross the blood-brain barrier by doing things like putting a second SCFB that hits the transferrin receptor that can attach them to the BBB and get them across. Probably more efficient it is to intrathecal delivery, which causes other issues, I guess, and it has other question marks. But it certainly we can make it very efficient as far as going to 90% of the body.
Very good. All right, we've got a question here from Christian, so I want to get to it. We've got a lull in the conversation here. In cases where the payload is DNA, are there any challenges in getting it into the nucleus?
So far, no. I mean, again, that could be size related, right? We've only done fairly small model systems right now. So when we get up to these really large genes, we'll see if we have any issues. But to date, we haven't.
Excellent. Great question, Christian.
So on that, does the transport system, I keep forgetting what you call it, but does that same transport system that gets it out of the MSC and into the target cell, does that also mediate nuclear transport, or is it just like by happenstance or unknown mechanisms?
No, you actually just daisy chain these things. So you have one peptide that'll get it to move out of the cell. You have another one that'll get it to move into another cell. You have another one that'll get it to move into the nucleus. And they don't always go in a row. Sometimes you have to put one on one end, one on the other end. That's part of the engineering piece of figuring out how to make this work well. That Robert's been working on is exactly where do they go, what order do they go in, things like that. But yeah, anytime you want to have a transition from one place to another, you have to add another element to it.
Yep.
Okay. So this is just reminding me of a conversation we had a couple months ago now, Jeff, with Neo Therapeutics, where Brian, what they're using is an engineered bacteria to target solid tumors and basically go inside of it that way. And the one thing I'd never considered with that approach is Pedro said the bacteria are living, and so they have the ability to actively target, as opposed to a protein case that is a viral vector or a lipid case that is a LNP. And so it's just kind of this passive event that takes place. But when you've got a living organism, it has the ability to like weave in and worm around different tissues. And so you're saying you've seen the same thing with this approach for you guys, where especially and so this gets interesting, right? So if you've got something that is in pretty dense, in a pretty dense place, a pretty fibrotic place, you guys are still able to get into that very dense environment to deliver your payload.
Yeah, I mean, there's always going to be exceptions, right? There may be places where we can't get into, but I think part of this is the cell can get part of the way there, but if it can't get all the way through, so say you have, like we looked at this in the tumor scenario, right? If you have a solid tumor, the cell can get to the outside like a CAR T can. One of the things, though, that the cells can penetrate maybe a layer or two in there, but our payload is thymidine kinase, which can penetrate even further in there. So we can get some penetration with cells, further penetration with our cargo. So again, in the context of killing scenario, that would be the case. In the context of something where we're trying to deliver to a solid mass of tissue that's, muscle or whatever else, we don't know exactly how far we can infiltrate that tissue, but we do think that we can infiltrate to a certain extent, and that whatever the payload is, there's a good chance of it going worth the rent.
Interesting. So I have some questions on the blood-brain barrier, and you mentioned that you don't have to use MSCs. Have you tried using any other kind of cell types, like myeloid cells, for example, or maybe a CNS like resident cell, like a microglia? Is that even possible? I wouldn't even know.
We haven't tried that. We've tried other cells. Yes, we started out with cell lines like Jurkat cells. We've used NK cells. We have used T cells, things like that. So NK cells can cross the blood-brain barrier, but for those we may have to gene edit out to the killing capacity, because in an allogeneic sense that may not be the best way to go. But yeah, we can use several cell types. MSCs are good because they're a very well-known cell, and because they're so easy to grow and transduce so well. So they're probably going to be a workhorse for the vast majority of things, but there's always going to be reasons why another cell may be preferred.
Yeah. That's very interesting that you're turning an MSC into a cytotoxic cell type. That's pretty cool. It's a CAR T cell, but it's not a T cell. It's an MSC. That's pretty cool.
Right. So it's got the benefits of the CAR T without some of the drawbacks of the CAR T.
So what are some of the drawbacks you avoid? Probably things like cytokine release syndrome and things like that. Are they not as robust like that?
We may. I mean, that it depends on how much of those responses are from the T cell themselves versus the killing of the tumor. Some of those side effects come from the tumor being destroyed, right, itself. So, but anything that's directly related to the tumor or the T cell, yes, we would avoid. The big one for allogeneic use is just not having to do the gene editing, having the durability, because right now we're not seeing really good durability in the allogeneic CAR T realm, right? So we think we can do a better job there. I think ours is not really well tested, so it's hard to say we can do everything better. But we have reasons why we think we'll have some advantages. Like I said, and it could be just in niche areas. So in the CD19 context, we have the advantage of not killing so many B cells. We think that's an advantage, right?
Sure.
That may not be as relevant in something like multiple myeloma.
Right.
So it depends on what the target is and exactly how many endogenous cells you're hitting with the target versus hitting with hitting the cancer.
Yeah. Okay. So you mentioned that you don't use genetic editing, but the actual therapeutic payload is a DNA base that you do genetically edit these cells, or do you load them with the peptide therapeutic?
No, we're gene modifying, but what we're not having to do is take away we're not having to knock in the TCR, right? Things like that. We're not having to do things that result in the therapy, causing a lot of damage to the allogeneic, background.
Sure. So it's like you deliver the therapeutic payload to your cells, and that's the one genetic edit. And that's good. Yeah.
Very good. All right, we got another question here from Stuart. Let's bring this in. Oh boy, with MSCs, how efficient is the tissue-specific retention with your models? Or with your modifications? Is it true that standard MSCs are very short-lived? When introduced IV, my recall is that they become trapped in the lungs in first pass and then are undetected after 24 hours.
No, I mean,
Brian, your response.
Yeah, people have been able to find these for 4 to 6 weeks, right? So, I mean, we don't have a lot of models yet that look exactly how long lived they are and how efficient the system is yet. Like I said, those are some things that we're still working on, but we do think the life span of these in vivo and allogeneic sense is enough to get what we want done. So it's enough to reach the target, find those, and then be able to deliver the payload. And then, then they can die off if they want to, right? We don't have to have them around for too long. Part of the reason normal MSCs dies off so quick or go to the lungs is because they aren't being targeted, right? They're going in and they're doing what like a virus does. They're just kind of inherently going where they go, which is oftentimes to the lungs. But when you target them, I think what we're seeing is they're probably going to have better lifespans because they aren't just going to the lungs. They're going where you want them to go, which is typically to a tumor or a specific organ, whatever it is. And we've shown that we can get them to home very, very well in vivo. So.
Excellent. Well, Stuart has a follow-up question here, so we'll get to that right here. A follow-up question: what is your advantage versus other novel targeting methods, such as engineering MSCs with non-signaling cars. Good gracious.
See if I understand that right. Put that one up again. Let me read that one again.
Yeah.
What is your advantage versus other novel targeting methods, such as engineering MSCs with non-signaling cars?
Well, I mean, I think our advantage over other systems right now is that we are able to target, right? The other systems that people are using are typically the viruses or particles, one or the other. And those, even though people have tried to get them to target, just don't target well, right? That you can't escape the natural tropism of viruses very well. And you can't really make LNPs do anything other than just swim around, right? They don't get targeted very well. So the difference is, we're actively targeting and actually making them go someplace. Now, there's other ways we could do it with MSCs. We've actually thought the same thing too. We don't have to use an SCFB, right?
Yeah.
We can use hormones. We can use other things like that. So there are other ways to target them. Those aren't bad, right? Those would work potentially equally well, or sometimes maybe better. It really depends on what you're going after and how you best target that particular cell type. In our case, the ones we're looking at, for the most part, we've seen some really good specific antigens we can target with an SCFB, but that may not always be the case. We may have to go to other methods for other indications.
Yeah. So in my second postdoc, which don't ask me why I did 2 postdocs, but in my second postdoc, one of the big questions that I was looking at was using, or it was more like a B cell studying and how we get like chemokine reservoirs in tumors. But along my research journey, I ended up kind of stumbling across this idea that in autoimmune disorders, there are a lot of like unique chemokine gradients that are created around the actual inflammation site. And people have tried to, there's very similar things in solid tumors, and you can actually express things like, I'm going to botch the names of these receptors now, but things like CCL or CCR13, I think, or there's like chemokine receptors that you can express onto T cells to have them naturally kind of home to areas of inflammation, hopefully the tumor. Right. It would be a very similar thing with this, where you wouldn't need to use a short chain variable fragment. You could use a chemokine receptor or some other kind of like homing mechanism. And then, that would maybe be the extracellular domain, and you would still have your systems like, inducible expression system on the intracellular part.
Yep. Yeah, we're using the SCFE because, again, it's a known entity. It's worked pretty well for these. We have some already. We already had a CD19. That was kind of our model system for everything. So we were able to use those and test the system, but we've already kind of looked at some of the other options outside of that. I think chemokine receptors is one that's, especially in oncology, that's definitely an option for us. There's other areas where there may be just better and, smaller things. SCFE still take up a certain amount of real estate, right? So if we want to limit that, if we have a lot of payload we want to carry, we need to limit real estate in the system. We may have to go to something other than SCFE for that reason too. So I think right now it's, we're doing what is, kind of cargo 1.0, right? We know this will evolve over time and get, we can have better versions of this down the road. And some of that may be different types of signaling or trafficking type mechanisms.
So why do you think that, you mentioned that there are other people who have been doing this? What is unique in your case?
Robert. So my co-founder and his brain just doesn't work like mine. It's a lot better. It works, especially on some of this, how to engineer this to make it work. And I think that's really the secret sauce, is what he's done on the engineering to make this work. Because like I said, other people have tried it in similar ways, but not the same. And they haven't been able to get kind of the mechanisms to work correctly, where you can get the combination of, you've got to get homing and migration first. You've got to get that. Then you have to have something to induce the production of payload, or the aggregation of payload and the transport mechanism. And then you actually have to get it to transport correctly. And then you have to have something functional on the other end, right? So we've been able to show that we can do all that. And that wasn't easy, right? That took time, and it took ability to figure it out. The nice thing is, now that we have that mechanism worked out, we can just kind of swap things out, right? When it works for one protein, it works for another protein pretty well. All you have to do is, okay, let's swap the sequence, swap the targeting, and now we can do something different with it. Same thing with the DNA. Now that we have it worked out, okay, we're delivering single-strand DNA. So we can do for SMA, we can do for DMD, right? We just swap out the DNA, we swap out the target, and we can have a new therapy. So But it did take quite a while to work out exactly how you make it work and how all those things have to kind of happen in order. Where you're not getting spurious delivery where you don't want it, and where you're not getting the cells to peter out before they get where they're supposed to go, all those things. So yeah, there's quite a bit to the intracellular engineering to make it
it's quite the dance. It's not very simple when you actually break it down into the various steps.
Yeah, the goal is to try to make it sound simple, but it certainly is.
Right. Yeah, at the granular level, it's like, oh, there are like 7 or 8 steps that need to kind of take place in sequential order under direct control. Like, it's not very easy. So yeah.
Exactly. Yep.
Yeah.
So if we back up for just a moment, and again think about the applications that are underserved right now. So you mentioned near the beginning of this conversation, Brian, for 80% monogenic diseases, you're going to be able to use something else, but there is that 20% that's just not being served at all. What would be some examples of those types of diseases?
Well, I think one of the big ones that people are talking about right now is DMD, right? Duchenne's muscular dystrophy, and it is being served. The problem is, one is we've had a lot of problems with the AV, right, with toxicity of the AV. The other one is what they're delivering is actually just a small portion of the gene. They're using what's called micro or mini dystrophin, and those are basically truncated versions of dystrophin protein that are able to fit into AAV. The problem is they don't really provide the structural support required for the muscle. The one they're typically using in AAV has about 40% of the structural support of a typical muscle dystrophin. And what that means is you may give them the ability to use their lungs and breathe, but you still aren't going to give them the ability to walk, things like that. So we can put in a bigger gene. We could use midi dystrophin, which is about 8 kb and has 90% of the structural support of dystrophin, or we can go to the full length 14.2 kb dystrophin. So in areas like that, where there's been a lot of interest, there's been a lot of therapeutic attempts, and there's been some successful commercializations in the space even, they're still kind of lacking in really creating a therapeutic that gives the ability that you want it to give to the patient, right? It can help them, but it's not truly curative in a lot of ways. These are things that give them a better quality of life than what they've had, but we think we can do better. We think we can continue to move that forward. If you look at things like Rett syndrome, and there's a lot of others. We've been looking at a lot of things, cystic fibrosis. There's a lot of these things that are very large genes, but even more so, like I said, it's not just the size of the gene. They've got to be very carefully regulated, because if you don't regulate them, you can cause just as much damage by putting in a gene that's unregulated as you can by the disease itself. So there are several diseases where getting a 1.5x quantity of protein is just as bad as no protein, right? You're going to damage people badly. So you have to have a very tightly regulated which cells are producing it, when they're producing it, how much they're producing, all of that. So that takes a lot of regulation, which requires more and more genetic code.
So how does that work then if we're looking at something like Duchenne? You've got this massive protein that you need to deliver all over the body. How does that work then with regards to dosing of this type of approach, where you have literally a cell and gene therapy?
Yeah.
Like what does dosing look like compared to other modalities?
Yeah, I'll be honest, we just don't know yet, right? I mean, we do know that we can get it to go to specifically where we want it to go, but it's something like muscle, where you're basically trying to get to go the whole body anyways, right? It's going to take a lot of cells, right? And people have done this with MSCs. People have given billions and billions of cells as doses, so we know we can generate the number of cells. And will it be extremely cost effective? Not as much as we'd like, for one, where we need that many cells, most likely. I think the difference is we can deliver something that we think is a better treatment. And even if we need more cells, we can still deliver it everywhere in the body. It just, eventually we'll have to figure out how high that dose has to go. And, if it's, 100 million cells, it's great. If it's 1 billion cells, we can figure out how to get there. But yeah, for ones like that, it'll be tough. It's a little easier to envision how we do it for like SMA, right? Where you need to get to a specific motor neuron, which is, not very plentiful in a very localized area of the body. When you look at things like delivering to muscle or delivering to other areas of the body where it's pretty ubiquitous, dosing will become an issue for us.
So what does the expansion in vivo look like for the MSCs? Is there a potential for them to kind of balloon up based
Probably
on?
Not a lot, not like T cells.
Yeah.
I mean, for the most part, MSCs in vivo don't seem to expand a lot. People used to use them in regenerative medicine, trying to get them to differentiate. and we would see more of a one-to-one differentiation. We wouldn't see a lot of expansion in those cases either. So we don't think there's going to be a lot of in vivo expansion. So we do think whatever dose is required is what's going to have to be put in. We're not going to be able to have the body help us to expand those cells.
Right.
Okay. On top of that, there's a question here from Richard Jones. Thanks for your question, Richard. We just talked about DMD, obviously. So the other one that has a massive protein is cystic fibrosis. So what's the potential of delivering a normal copy of that?
Yeah, so it's one we're looking at. Again, I think that's somewhere in the 9 kb gene or something like that. So it's one we've looked at. We think we can do that. Again, I mean, we're right now still working on a lot of proof of concept. We are starting to develop a couple of assets and looking where we can, have the most impact. But and cystic fibrosis is one. We're talking to people that are already working in the space. I think one thing we're trying not to do is reinvent the wheel on every scenario, right?
Sure.
People that are working in cystic fibrosis already know where it needs to go, what gene needs to get there. They know a lot of stuff. So we're trying to work in concert with other groups that already have a good idea of what needs to be done. And we're just saying, hey, we have a way to maybe get it there, right? We have a delivery vehicle. We don't want to reinvent the wheel on all these therapeutics. There's a lot of knowledge out there and a lot of people that know what they're doing. We can just offer a delivery platform. So yeah, we think we can do it. We've talked to a few people in cystic fibrosis, and we think there's certainly a path forward.
Nice. Well, the other thing that I have heard, which might fall in with Stuart's next question, which we'll get to in just a moment, and anyone else, if you have questions, feel free to post them. But again, I think what's interesting, even with regards to cystic fibrosis, and the challenge that I've seen, and I remember at ASGCT a couple of years ago seeing a talk on this, is when it comes to cystic fibrosis, the challenge is actually delivering the vector, because in normal circumstances, you've got this massive mucus layer, and then underneath that, you've got kind of the top layer of epithelial cells, which are the current problem. They're not pushing the mucus away, but then underneath that, you've got the cells that are more stem, the stem cells that are actually going to be creating the next generations of epithelial cells. And the challenge is, how in the world do you get through all these different layers of cells to those actual stem cells to ensure that you're going to have sustained expression of the correct cystic fibrosis gene? And so potentially, right, with something like this, where you don't have just a passive protein vehicle or a passive lipid vehicle, you've got something that's alive, that's able to kind of worm its way through different layers of tissue. Do you see that being something that could be a competitive advantage?
To be honest, to be determined. I'd love to say yes, but we just don't have the data yet. Yeah, I mean, we know that MSCs have the ability to kind of migrate through stuff, right? In general, right? They can migrate and get outside the blood vesicles. They can do things like that. Whether or not they can get through the mucous membrane, that's part of the problem there. We don't know. Whether or not we could put it in some sort of inhaled form to kind of come from the inside of the lung going out, we don't know. All good questions. So we have, what we do know is we've got a great delivery vehicle. Exactly how to get it where we want it to go in all cases like this, where we have, something that seems to be a substantial layer for any kind of delivery system. Could it impact ours too? Yes, definitely could. Right? We don't know that we can get around it. Another one for us in this one in particular is, in a lot of cases, we don't need to integrate our delivery. Right? We can do it in episomal delivery is good enough. These cells are around a long time, and we just need them to get it in there, and for the cells that are existing to be able to do this. In something like cystic fibrosis, as you mentioned, we really need to get into the stem cell. We need to have an integrated DNA, because we needed this to be able to be a long-lasting thing down in their progeny. So for us, that is another, or for any delivery system, right? It's another element that you've got to get through, is how do we integrate this into the genome, where it's not just the cell that we're getting it into that's going to be affected, it's all the downstream progeny that are going to be affected. Yeah. So it's something we're looking at when we look at, doing HSCs, when we're doing any sort of stem cell, because we want to affect downstream progeny.
Right. And again, just with regards to the comment that Stuart just put in there, with regards to the advantages of AAV being that penetrance into solid areas, with MSCs, right? Again, the theoretical benefit here being you've got something that's a bit more targeted in that it actually has the physical ability to worm its way.
Cells can do that, but they don't do it automatically. You get some cells will do it more likely than other cells, but I'm not super sure how equipped MSCs are to really break through tissue like that. Like
Okay.
bacteria are smaller. They'll home to hypoxic regions. Like bacteria kind of do that naturally, but a MSC is humongous compared to a bacteria, and they don't tend to like just like chew their way through tissue. So
one thing we have thought about for that reason for things like this and fibrotic tissue is being able to actually have certain cells go in and deliver enzymes that will eat the way through, and then other cells that would follow that with a therapeutic payload, right? So we can actually have MSCs that do nothing but deliver enzymes into the interstitial space to chew up mucus or to chew up something else, right? As long as we know what the extracellular matrix is we want to chew through, and we have something that can chew through it, we can deliver that, right? We can get it again, target the mucus, try to get rid of the mucus first as the first level of delivery, and then target the cells underneath that secondly.
Very good.
I'm wondering, like, could Neob do this? Because the big thing here is like we can engineer in homing mechanisms. Neob is relying on like the bacteria's intrinsic properties to home to the tumor microenvironment. Just like endogenously, they have like inherent behavior that kind of does that.
Mm-hmm.
But I'm wondering if this is an advantage even over that, because you can say, hey, we can basically do what Neob is doing, but not just to tumors, to anything really. If we can find a target for these things to go after, we can have them do what this therapeutic platform does, but just kind of like wherever we want it to go.
Right. Yeah, and again, it's about specificity. That's the key, right? I mean, if we just target mucus, then that could be a real problem. If you're eating up on mucus, that's not something you want. But if there's a way to target the specific area and say we just want to have enzyme digestion of kind of the stuff that we don't want over a certain period of time, just to basically open it up and give us a reason to then engage the cells underneath, that may be a way to do it. Again, kind of shooting from the hip here. We've thought about some of these things a little bit in the area of fibrotic disease. But I think there's a lot of areas that we could look into and how to continue to expand the options for us.
Very good. Okay, we've garnered a couple extra questions here, so we'll just run through those. Sorry, the way that our studio is set up, sometimes it doesn't show us who the person is. So thank you for your question. Nameless
Rachel.
person that you cannot see right now. Rachel. Perfect. Rachel has a question. Could you please speak to cargo delivery in NK cells and how finicky they are? What delivery mechanisms are leading and which ones have been shelved?
Finicky.
So we haven't worked with NK cells a lot. We mainly started looking at NK cells because of their ability to cross the blood-brain barrier. And we thought it may be a good cell because instead of having to engineer that in or do intrathecal delivery, we could use NK cells. So we basically tried it just to make sure we could get it to work. And, again, we haven't done a lot of optimization. We don't have high efficiency systems, things like that. I don't know that it would be a routine cell for us. But it's one of the ones we wanted to try for that specific reason. And we basically said, hey, it looks like it'll work. It looks like we can engineer them. It looks like they can deliver something. But we didn't go beyond that. So again, we're a small team. We're 5 people. There's only so much we can do. And right now that wasn't on the radar screen for us to move to. It's more about making sure we can deliver multiple different types of payload, continuing to expand on size of payload, things like that, and looking how we can better target through different scFVs.
Very good. Okay, and then we've got another question here from Maria, who is coming in from Greece. Thank you for coming so late in the day and with your question. And your question here is, would repeat application of MSCs activate an immune response? Yeah, I know we talked about this briefly a little bit earlier, Brian, but if you could recapitulate, that'd be great.
Yeah, it could. In past, people have done this in allogeneic sense, and they haven't seen too many problems with repeat doses of MSC. So we don't think it's going to be a big issue. But the goal would be, if it is an issue with somebody, we would move to another donor. So our goal would be to have multiple donors that we stack up. We make master cell banks, and that we would be looking for one donor to be used for a first time delivery. If we saw any sort of immune reaction, if they needed a repeat dose, we'd go to a different donor.
Cool.
Yeah. So and there isn't a potential for any kind of like pathological immune response. It would more just be like an immune response to reject the therapeutic.
Yeah, it would be a rejection.
Yeah.
We don't see. I mean, MSCs don't have any sort of like graft versus host type of capability that we've never seen it, and like it's ever been documented. There have been a few small safety issues with MSCs, but nothing significant. So we think that the bigger issue is just rejection, that it wouldn't
Yeah.
be they'd have to move to another donor for that reason.
Right. So even Christian, you just put in a comment asking like, what would the immune response be here? So that's really interesting. We haven't really seen anything in the past with regards to MSCs this way, and and we have the benefit of basically being able to have multiple different banks, so that if you end up having a response, you can just move on to the next bank that your immune system hasn't seen before.
Right.
Interesting. Okay. Stuart coming in with another question. Thanks for all the questions, Stuart, here. Or would you go for an auto approach? I'm assuming he's kind of contrasting allogeneic versus autologous here.
Yeah, I mean,
what's the thought there?
I mean, we certainly could, but one of the benefits of our platforms is the economies of scale, right? Being able to use something like MSCs and get them down to a really low cost, because you can grow so many of them. We don't think doses will be extremely high in a lot of cases. And so the cost factor is going to be the big one. Could you do it auto? Yes, there's no reason why you couldn't, right? But it may be cost prohibitive for a lot of these. If our goal is to make these a more usable, more accessible type of therapy, auto is going to be an issue with cost.
Yeah, and this is probably like it would be very beneficial in terms of consistency as well. You wouldn't want to be having to have because you can make like a master cell bank of your MSCs and use them across different patient populations. To do it patient by patient, like you're looking at potentially like huge variations in the downstream expression of this stuff and all kinds of consistency problems. Whereas with a single master cell line, like master cell bank, you're guaranteed the same sort of like dynamics throughout.
Yeah, and people may behave slightly different, but it's going to be a lot bigger issue if you're doing it. The manufacturing issue is going to be bigger on that side. Because the nice thing about allo in this sense is like any other allo, right? We can make a big bank. We can make a master cell bank of one donor MSCs, and then we can make multiple working cell bank, each for a different disease type, right? Each donor vector, and each one of those for disease X, one for disease Y, one for disease Z. The same master cell bank, and then you can go to master cell bank 2 and do the same thing across the board.
So this is a naive question, but is there any other kind of therapeutic platform that uses this kind of like it's probably like a syn notch type of thing where you're going to get the receptor activation that leads to a release of a transcription factor more than likely? Like what is the actual mechanistic cascade that happens upon CAR binding, or I guess
Yeah, the CAR binding, it's similar to other mechanisms, right? We're using basically an inducible promoter. So the nice thing is we don't need to have a really long internal domain on the CAR. We just need to have some sort of inducible promoter where you get a conformational change and you induce then a promoter to generate the next step, right? So there's a few different ones we can use, but we don't need to have like a second and third generation CAR because we don't need all the the CD3 zeta and all the CD28 inside. We basically need first generation CAR. So again, not as much real estate in the vector, fairly simple device. We need the extracellular recognition, then we need one small conformational change inside.
Right, and it relies on an endogenous transcription factor in the cell. You don't actually introduce a synthetic like system.
Correct.
Yeah.
Correct.
Super cool. Okay, we've just got a couple questions. We've just got a couple minutes left here, and there's just a couple of questions I would like to ask personally before we leave off. So I guess from all of the research that you folks have been able to do so far, Brian, what have you seen that got you most excited?
Well, when we did the animal data and we basically saw for the first time that it all worked, right? I mean, that was because we were kind of holding our breath to say theoretically it works, in vitro it kind of works, but in vivo, can we get this to work? And we were using model systems, right? We were producing luciferase. But whenever you do whole body imaging and all of a sudden you see that, okay, the cells got where they were supposed to, the luciferase is there, all of a sudden we see it shining, and then you do histology and say it actually is where it's supposed to be. It's inside the cell that we want it to be in. And you see that all that theory kind of came into evidence. That was the aha moment for us, right? Because until then, we talked a good game, but we didn't know if we could actually make it work. But when the evidence was there and we saw it actually functionally, that was great. That happened, early this year. We had been working on it since about September, so it took us about 5 months, 6 months, something like that, to get the really good functional data that said, yeah, this works.
Nice.
Right on.
Now, have you done any head-to-head comparisons with like a traditional delivery vector, like an AAV or an LMP, and see
Not
like
yet.
more
It's
specificity?
definitely in the radar screen to do.
Yeah.
Just been bandwidth trying to get something like that.
Yeah,
done.
it's
Very good. Okay. There's just one final question here from Stuart. Well, it's more of a comment, so maybe you can chat about it, Brian. So I had auto MSCs proposed to me for manufacture despite COGS and consistency. It is a consideration for some indications.
Yep. Yeah, and there's some people have done auto MSCs, right? It's been kind of a niche area because, I mean, 30 years ago, people started with auto MSCs, right? That's kind of how it started, but it very quickly transitioned to an allo type of therapy because people saw that it was doable, right? And the COGS were always made sense that way. But there have been a couple of people over the years that have done auto MSCs. And for us, I don't think it's a necessity. I think the economies outweigh any sort of issues you would have with doing an allo therapy. And so far, we haven't seen any. I mean, again, we haven't gone very far. We haven't done our first in human yet, where everything's in animal studies and in vitro work. But we haven't seen any issues that would make us say that for us, allo is going to be a problem.
Nice.
Yeah. And the auto MSC makes sense for like regenerative medicine where you wouldn't want it to be rejected ever. But for things like this, it's kind of like, yeah, you can get like 3 or 4 weeks, whatever. Right.
Yeah, that's all we need, right?
Yeah.
Rejection is fine. And actually, like I said, maybe a safety mechanism to a certain extent.
Yeah.
If we either don't have a suicide switch or that's not quick enough, we know these cells are going to be rejected over time.
Yep.
Perfect. Well, we want to be respectful of your time, Brian. We appreciate you coming today, and thanks to everyone else who came and listened and asked questions. It always makes for a more interesting conversation than just Jeff and me coming up with conversation topics.
Hey, I have good questions too, okay?
Allegedly.
According to you.
If you guys don't know who I am and just saw the post, then here I am.
Just to set the record straight, I don't look like that.
I don't think I look like that. I don't look that good, actually. So.
Very
That's
good.
Funny.
Well, Brian, thank you for coming today. Thanks to everyone else for showing up. We appreciate your time, and we'll see you next week.
All right. Thanks, everyone.
Awesome.
Thanks, everyone. Bye.